Let's review a little bit of rational functions. The definition is a rational function is given by a quotient of two polynomials, borderline p of x over q of x. And of course, q of x cannot be zero. And as I said, p and q are polynomial functions. The domain of the rational function, all real numbers except for the zeros of q of x, namely those numbers that make the denominator zero. In other words, avoid zero in the denominator. Notice that I have three basic examples here. The numerator doesn't make a difference, so f of x equals whatever over x minus 1, I just put 12. So here, of course, when the denominator becomes 0 when x equals 1. So the domain of this one will be all real numbers except 1. In other words, from negative infinity to 1, union 1 to infinity. Here I have 12 over x squared minus 1. So x squared minus 1. Therefore, what is the domain? The numbers that make the denominator 0, in this case, will be plus or minus 1. So the domain would be all real numbers except plus or minus 1. Okay. On the other one, the last example, f of x equals 12 over x squared plus 1. Notice that x squared plus 1 is prime. You cannot make it 0. So in this case, the domain will be, of course, all real numbers. There is no exception. Just a quick overview of domains. Let's now discuss asymptotes. Let's go ahead and discuss. An important topic of rational functions will be asymptotes. Asymptotes can be seen like quote unquote walls or lines that hold the graph, doesn't let the graph continue their path. So we will experience three types of asymptotes, either vertical asymptotes, horizontal asymptotes, or oblique or slant asymptotes. Just out of, we do not discuss oblique or slant asymptotes in college algebra, so I'm going to read this one. If and when you move to pre-calculus, then we'll talk about slant or oblique asymptotes. So we have two types, either vertical or horizontal. Always remember that vertical lines are always of the form x equals a number, x equals 2, x equals 3, x equals -5. And horizontal lines are always of the form y equals a number, y equals 2, y equals -5, y equals -10, y equals 20, etc. So I have two pictures here. By the way, each graph experiences other type. I mean, anyway, so I'm just showing here vertical asymptotes. Notice that the graph comes from negative infinity to infinity. So what the graph is trying to do is wants to continue going to the right-hand side. However, this invisible line here, x equals c, pushes the graph to go up. So the closer I get to this number, x equals c, the graph either goes to positive infinity or down to negative infinity. It has to go somewhere. So either continues to the positive infinity or to negative infinity as I keep getting closer to the number c. The closer I get, the function goes all the way crazy up, all the way crazy down. That's what the vertical asymptote means. X equals a number. We never, never, never intersect a vertical asymptote. So anyway, so here, once again, so it has to jump because it's not defined at this point. So now it comes from the positive infinity, it continues. Oh, this one wants to continue going down. However, it experiences another line that pushes the graph down. So this one, as I get closer to, let's say 3 or 4, x equals 4, so the function continue going to a negative infinity. Okay, so that's what the vertical asymptote means. So the closer I get to a particular number, the function goes either to positive infinity or negative infinity. By the way, this one also experiences a horizontal asymptote, but speaking of horizontal asymptotes, in this case, y equals b will be a horizontal asymptote. This one, horizontal asymptotes, they cap the function, does not let the function to continue growing to a crazy number to infinity or negative infinity. By the way, vertical asymptotes is the behavior when I try to get to a very close number, either from the left or from the right. So every time we talk about vertical asymptotes, what is the behavior of the function as I get closer to a particular number? Horizontal asymptotes, what is the behavior of the function as x goes to negative infinity, the number gets very, very, very small, or the number gets very, very big. Does the function keeps growing or it gets capped, it gets held at a particular number? So for example, here, let's say that this number is x equals, I don't know, 2. So the bigger the x, the function will attempt to get to 2 and it dies at 2. It will be 1.99999 and it gets there, stuck there at 2. Likewise, when x goes to negative infinity, the function continue going here and it will go to 2.0000001. It will try to get very close to 2, but in this case, never touches. By the way, we might be able to touch or even intersect horizontal asymptotes. More than several cases, we will intersect the horizontal asymptote. We will never, ever intersect a vertical asymptote. So let's recap. Vertical asymptotes, what's the behavior of the function as I get closer to a particular number? Horizontal asymptotes, what is the behavior of the function when I go to the infinity? So a good way to see the horizontal asymptote, let's look at these two graphs. If I have one like this, if I have a parabola like, going like that, and this guy is 1, or I have a parabola like what? Let me flatten down here. That would be a classic example, or in this case, as x goes to negative infinity, the number gets very, very small, the graph goes to positive infinity. Keeps growing without bounds. Likewise, when x goes to positive infinity, the function keeps growing with no bounds. So this one will not experience a horizontal asymptote. There is no cap to the graph, literally. On this one, as x goes to negative infinity, the graph will continue going like this. It will be closer to 9.99999. This one doesn't actually touch 10, y equals 10, but we will say, okay, it will approach 10. When x goes to positive infinity, likewise, the function will be capped at 10. So no HA, yes to HA. What is the horizontal asymptote? Y equals 10. Before we continue the discussions, let me review, of course, the definition of rational function. As I said, it's the quotient of two polynomials, P over Q, P of X over Q of X, where Q of X is not 0. So talking about vertical asymptotes, let's go ahead and so see the definition of vertical asymptote. As I mentioned before, x equals c or x equals a. What is the behavior of the function when we approach a particular number? In this case, when we approach a, the function either goes to the positive infinity or to negative infinity. And then what is the definition of horizontal asymptote? Now this is the end behavior. What happens when x goes to positive infinity or to negative infinity? If the function approaches a fixed number, then the line y equals b will be your horizontal asymptote. So how do I find vertical asymptote? Let's go ahead and talk first about vertical asymptotes. So how do I detect or find the vertical asymptotes? Before I do that, let me go here to page 420. Of course, the domain of a rational function, given all the real numbers except for those numbers that cause the denominator to be 0. We went over that already. And then how do I find vertical asymptotes. Okay, here we say that the vertical asymptotes will be those numbers that cause the denominator to be 0 in its simplified version. Sometimes those restrictions will be, if they are not asymptotes, they are called removable discontinuities or holes. We'll go over this in a moment. Okay, so let me stop sharing the document. So this is my definition of vertical asymptote. It has to be in its lowest form, will exhibit a vertical asymptote at the zeros of Q of X. Let's go ahead and do a couple of examples. Let's start with these 3 examples. Example number 1, f of x equals 7 over x plus 5. I would like to identify the domain and any VA vertical asymptotes, if any. Once again, the domain of the rational function, any number that, or real numbers except the numbers that make the denominator 0. In this case, of course, when x equals -5, it will be 7 over 0, so that's undefined. So my domain will be all real numbers except -5. And this one will exhibit one VA at, so it's all real numbers except -5. That's the domain. And then the range, sorry, the VA will be x equals -5. Why? Because x equals -5 is the 0 of the denominator. Okay, so it's as simple as that, as straightforward as that. So I mean, all real numbers except -5, therefore the VA will be x equals -5. So what do we know about this graph? We don't know much and we know a lot. We know that, of course, that there will be a wall here at x equals -5 that will hold the graph. So this graph, we don't know the behavior. So this graph might come from here and then will attempt, so it goes to positive infinity, or maybe the graph comes like this, but then it will be shooting down. We don't know yet. And then once we hop the -5, x equals -5, so either starts from the infinity and goes down, or comes from the -infinity and goes up. We don't know yet. But having this line here will hold the line, will hold the graph, and will split the graph into subgraph. I mean, one piece here and one piece from -infinity to this asymptote, and then another piece from the asymptote to positive infinity. Okay, so remember, as we get closer to -5, it will go to positive infinity or -infinity. We don't know yet. The second graph, okay, x minus 12, blah, blah, blah. How do I find the domain? Well, first of all, we have to factor the denominator. So this is equals to x minus 12 factors of -8, that gives me +2, perhaps x plus 4 times x minus 2. Plus 4 minus 2, that's +2. Okay? So in this case, my domain will be what? The domain will be all real numbers except, what are the zeros? -4 and +2. -4 and +2. And this one will exhibit 2 vertical asymptotes, one at x equals -4 and the other one at x equals 2. The numerator is x minus 12, so there is nothing to simplify. I'm going to erase this here. I have a light bothering me. So this function, example number 2, a very rough, would be something like this. This one will exhibit 2 walls, one at x equals -4, and the other one at x equals 2. And once again, we don't know how this thing will look like, but we know that as we get closer to -2, the function will go all the way to +infinity or will come down to -infinity. Then when we pick up again, it will come from the positive infinity down or from the negative infinity up. And continues like that. And of course, when x equals 2, we have the same behavior. Either we go up or we go down, or you get the idea. Okay, so this one will exhibit three chunks. One graph will be here, then another one here, and lastly another one here. Last but not least, oh wait, I forgot about writing here. So the VAs would be x equals -4, x equals 2. So two vertical asymptotes, one at x equals -4, the other one at x equals 2. Now, example number 3, very similar to this puppy. So what is my domain? Well, it's the same denominator. So the domain is all real numbers except -4 and comma 2. However, how do we find the VAs? That was x minus 2, x plus 4, x minus 2. Notice that the way this function is written, it is not in its simplest form, in its lowest form. If you remember the definition from a couple of minutes ago, notice that x minus 2 and x minus 2 can be simplified. So this function in its simplest form, in its lowest form, is 1 over x plus 4. Thus, this function, the VA, is only one vertical asymptote where x equals -4. Even though we have two exceptions in the domain, we only exhibit one vertical asymptote. Why? Because the function can be reduced. We will say that at x equal, notice that we simplify x minus 2. So when x equals 2, the function will exhibit a discontinuity. Okay, so the function will exhibit a discontinuity or a whole at x equals 2. Bottom line, if we simplify, we are trading one asymptote for a discontinuity or a whole. So that's all it is for vertical asymptotes, very difficult. So I recommend to always find the domain, even if they don't ask us to. Find the domain and then find the VAs. They should go together all the time. So it's very straightforward. Just have to factor and attempt to simplify just to make sure one of those vertical asymptotes does not get traded off with the whole. Okay, so if I have two exceptions in the domain, I have to have two something, either two vertical asymptotes or one of those vertical asymptotes, or one of the vertical asymptotes got traded with the whole. So we'll have one VA and a whole or two VAs. If I have, for example, two exceptions in the domain. Hopefully that will help. Now, if you believe that finding vertical asymptotes was very difficult, I'm being sarcastic, finding the horizontal asymptote is even more difficult. Yeah, right. First of all, let me share a document here. If I know how to. Okay. Okay, so this is how we find the vertical asymptotes. Okay, this is the removable discontinuity. Occurs when the graph of rational function, if a is a 0 for the factor in the numerator and denominator. If we can simplify it, then it is a removable discontinuity. Otherwise, it is a vertical asymptote. Okay, so for example, here in this example, x minus 2 over x squared minus 4, notice that the denominator factors as x plus 2, x minus 2, we may simplify x minus 2. So we exhibit the vertical asymptote at x equals -2 because of x plus 2, and then a discontinuity at x equals 2. This is what they call the whole. And if you see the graph, we'll do a couple of examples. Now, finding horizontal asymptotes. It's a lot of blah 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 blah. By the way, this is a slant or a oblique. An oblique asymptote is diagonal, the green one there. How do I find horizontal asymptotes? It's or here, we only need to look at the degrees of the numerator and denominator. By the way, this rule only applies if you're looking for horizontal asymptotes of rational function. The whole discussion is about rational functions. Of course, other functions exhibit either vertical asymptotes or horizontal asymptotes, but this is not how we look at them. This rule only applies if you're dealing with the rational function. So notice that the only thing we need to look is the degree of the numerator and denominator. So I'm going to stop sharing here. So this is the rule. So first of all, f of x is p over q, division or quotient of rational function. Let's call n the degree of the numerator and m the degree of the denominator. Likewise, let's call a the lead coefficient of the numerator, and let's call b the lead coefficient of the denominator. Then, if the degree of the numerator is higher than the degree of the denominator, we just simply said there is no horizontal asymptote. If the degrees are the same, then we look at a over b. We take out the quotient of the lead coefficients, and then if the degree of the numerator is less than the degree of the denominator, then we have a horizontal asymptote at y equals 0. Okay, so I'm going to give you one weird example, and then I'm going to start changing things. So remember, n, the degree of the top, m, the degree of the bottom, a, the lead coefficient of the numerator, b, the lead coefficient of the denominator. Okay, it's either no HA, y equals 0, or the quotient of the lead coefficients. So let's take a look at this example. F of x equals 5x to the 7 plus 2x cubed over 3x to the 4 minus x. That would be simple enough. Of course, the numerator is a quotient, is a polynomial, degree 7, lead coefficient 5. The denominator is a polynomial, degree 4, lead coefficient 3. Of course, f of x is a rational function because it's a quotient, a division of two polynomials. So degree 7, degree 4. What can I conclude? Well, in this case, since the degree 7 is higher than the degree of the denominator 4, we simply said that this one has no horizontal asymptote. What if this guy was 6? Same thing, same thing. What if this guy was 5? Still the same rule applies. That the numerator, the degree of the numerator is higher than the degree of the denominator. So this one will have no horizontal asymptote. Just a quick comment, when the degree of the numerator is higher by 1, just like in this case, we say that the function doesn't have a horizontal asymptote. However, it will have a slant or oblique asymptote. If the difference is by 1, when the numerator is higher by 1 in the degree, then we have a slant or oblique asymptote. But we don't care so far. So now in this case, this guy there is 5x to the 5 plus blah, 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 3x to the 5. So now the degrees are the same. Since the degrees are the same, we look at the lead coefficients. The lead coefficient of the denominator is 3. Here is 5, so this one will exhibit a horizontal asymptote at y equals 5/3. Why? Because the degrees are the same, so we look at the lead coefficients. If this one was like that, that means that the degree would the horizontal asymptote will be 5/1, which is just 5, because there's an invisible one here. If I have a negative here, it will be y equals -5. As simple as that. Okay, there is no, this is like that. The function will be x to the 5 over x to the 5 minus 1. That will be y equals 1. Invisible 1/1 will be 1. Okay, so it's like that. If the degrees are the same, then we look at the lead coefficients. What if the function was, where was I? What if the degree here is 4? Now the degree of the numerator is lower than the degree of the denominator. So what do we say? HA at y equals 0. This guy is 2, this guy is 3. Of course, HA is 0. So long as the denominator, the degree of the denominator is higher than the numerator, then the function exhibits the horizontal asymptote at y equals 0. Okay. So let's do one big example. Let's see if we can do it. F of x equals, f of x equals, f of x equals. X plus 5 or x squared minus 25. Okay, let's go ahead and find the domain. Let's go ahead and find the VA, if any, and the HAs, if any. The way things rational, we can only have one HA, if any. Okay, so in this case, we need to factor the denominators. So that will be x plus 5, x minus 5, and it will be x plus 5. Notice that the domain will be all real numbers except plus or minus 5. To find the vertical asymptotes, we need to look at the function in its lowest form. So in its lowest form, x plus 5 eliminate, will be 1 over x minus 5. What do I have? We will have one VA at what value? X equals 5. And we will have a discontinuity or hole at x equals -5. That's the one that we trade off. Okay, so we'll have one VA at x equals 5, one discontinuity at x equals -5. For the HA, we need to look at the coefficients. Sorry, the degrees and coefficient, but the degrees first. The degree here is 1. The degree here is 2. Of course, the degree of the denominator is higher than the degree of the numerator. Therefore, this function will exhibit one horizontal asymptote at y equals 0. And that will be it. Let's try a second example. What if I have what if I have hopefully this one will, let's see, what if I have x squared plus x plus 6 over x squared minus 10x plus 24. We need to find the domain, any VAs, any HAs. First of all, let's go ahead and factor this guy. Factors of 24, that gives me negative 10 when I add them. 6 and 4, both of them have to be negative. So x minus 6 times x minus 4, negative 6 and negative 4, positive 24, negative 6 plus negative 4, negative 10. Okay, by example, so this one, factors of c, that gives me 1. That would be 3 and, no, both of them. Oh, never mind, that one does not factor. So let me change something here. Just to minus minus, oh my God, minus 6. The 7 here. 6 and then minus 7x. Okay, there you go. So let's see what happens. I force it. So factors of positive c, that gives me negative 7, negative 1 times negative 6, that would be positive 6, negative 1 plus negative 6, negative 7. So the numerator factors as x minus 6 times x minus 1, if I'm not mistaken. So now that we have everything factored out, let's look at the domain. So we need to avoid positive 6 and positive 4. Those are the two zeros. So all real numbers except when x equals 4 and when x equals 6. The VAs, can we simplify anything in the original function? Yes, indeed. X minus 6, x minus 6. So in its lowest form, it will be x minus 1 over x minus 4. So how many VAs do we have? Only one vertical asymptote. Where? At x equals positive 4. And then the function will exhibit a whole order discontinuity at x equals 6. We need to account for the 6 that we eliminated. So it's either a VA or a whole. So if we eliminate, it will be a whole. If we do not simplify, it will be a VA. And the horizontal asymptotes, well, the degree here is 2, degree here is 2. So the degrees are the same, so I need to look at the lead coefficient. Here is 1, here is 1, so 1 over 1 is 1. Therefore, we have a horizontal asymptote at y equals 1. And we are done. Okay. One more thing, let's talk about the intercepts, specifically the rational function. Well, it doesn't matter, back to basics. For how do I find the y-intercept? We always force x to be 0. How do I find the x-intercepts? We make the function equals to 0, y equals 0. Okay, so we simply plug in 0 in x to find the y-intercept. Now, to find the x-intercept, we will have to make the function equal 0. But remember, the function is a rational function. The only way that the function f of x equals p of x over q of x equals 0 is when the numerator equals 0. Just because we are dealing with rational functions, so instead of saying that the whole function equals 0, we can just simply focus on the numerator. So what can we conclude? So we just simply make the numerator equals 0, just because we are dealing with rational function. So let's just do 2 examples of finding the intercepts. So let's try these 2 examples. We're going to find the intercepts. Actually, let's call it intercepts. So for the y-intercept, we make x equals 0. This one is easy. We make x equals 0, so the y-intercept will be -5/81. 0 plus 5 is 5, 0 minus 81, -81. So the y-intercept in this case will be 0, -5/81. Okay? Let's see if we can mentally find the domain, the VA, and the HA. For the domain, we need to avoid seeing the denominator, so we need to avoid 9 and -9. 9 and -9, right? Do we exhibit any vertical asymptotes? The answer better be yes. How many? 2 of them. X equals 9, x equals -9, and x equals 9. Perfect. And the horizontal asymptote, well, the degree here is 1, degree here is 2. The denominator degree is higher than the numerator, so this one will exhibit 1 HA at y equals 0. Okay, and then what it will be I should have talked about the x-intercept first. That was the whole idea. The x-intercept, in this case, is only 1. We make the numerator equals to 0. So therefore, x plus 5 equals 0, x equals -5. So that's my x-intercept at -5, 0. My y-intercept, the x-intercept, I said that the domain was all real numbers except plus or minus 9. VA's x equals -9, x equals 9, and HA y equals 0. Okay, nice. Okay, so I added more stuff. So let's look at example number 2. Let's just focus on the intercept first of all. Y-intercept. Okay, so y-intercept x equals 0. So when x equals 0, this will be bye-bye. This will be bye-bye, this bye-bye. So it would be 0, -48 over -2. Right? And we know that one will be 4. So 0, 4. Okay. What about the x-intercept? My numerator equals to 0. My numerator is okay. It's going to be a little bit. Well, normally we look for the domain first. So I'm going to contradict myself in a few. So my x-intercept, my numerator, 3x squared minus 48 equals 0. We can factor out the 3. It would be x squared minus 16 equals 0. So we divide by 3. So x squared minus 16 equals 0. So x plus 4 times x minus 4 equals 0. So x equals -4, x equals 4. Okay, so for now, the y-intercept will be 0, 4. And my x-intercept will be -4, 0 and 4, 0. Okay. Normally we look for the domain first, vertical asymptotes, horizontal asymptotes, and then we look for the intercepts. I should have followed the steps, because in this case we have an issue because I did it on purpose. Let's go ahead and look at the domain first. If I were to look for the domain, we'll have to factor. So this guy factors as 3 parentheses x plus 4, x minus 4. And then the denominator, factors of -2, that gives me -1. That would be x minus 4 times x plus 3. Yeah, -4 plus 3x, -1x. -4 times positive 3, -12. Okay, so now first, let's just do this one properly. Sorry about that. So once we do that, we always look for the domain. The domain here will be which numbers I need to avoid. And it would be all real numbers except -3 and 4. That's your domain. Do we have any vertical asymptotes? Well, we need to look to see if there is anything that could be simplified. So x minus 4 gets simplified. So the VA will be x equals -3, and there will be a discontinuity or echo at x equals 4. HA, do we have any? Yes or yes? Degree here is 2, degree here is 2, same degree. We need to look at lead coefficient. This is an invisible one, 3 over 1 is 3, so HA at y equals 3. We have the y-intercept. Well, the y-intercept is when x equals 0. The y-intercept will be 0,4. What about the x-intercepts? For the x-intercept, we make the numerator equals 0. So I recommend to use always the simplified version. So here, when 3 times x plus 4 equals 0, we divide by 3. So x plus 4 equals 0. Therefore, x equals -4. So we are going to have one x-intercept at what? At x equals -4. So -4, 0 would be my x-intercept. Notice that if I use the numerator without simplify, so it will be, of course, 3 times x plus 4, x minus 4 equals 0. So we'll have either x equals -4 or x equals 4. So in theory, we'll have two x-intercepts. However, we know that 4 is not part of the domain, so eliminate this one. This is why I said it's better just to use the simplified version to work from this point forward. And that will do it. So given a rational function, we know how to find the domain, vertical asymptotes, horizontal asymptotes, y-intercepts, and the x-intercepts. Okay? And also, let's recall that we will never, ever, ever intersect the vertical asymptotes. We might intersect the horizontal asymptotes. So later on, what we will do, we will ask ourselves, do I intersect this asymptote, yes or no? So we need to answer this yes, no question. Do we intersect the horizontal asymptote, yes or no? Vertical asymptote, we don't have to worry about it.